Hello everybody, welcome back to Deviations. In today's video of single variable calculus, we will be covering a new topic called concavity. This is going to be really important for expanding our abilities to sketch graphs with high degrees of accuracy. So again, differentiation is a prerequisite for understanding this topic. So if you are not comfortable with that, I recommend that you go back and watch some of my videos on Unit 2 differentiation. With that said, why don't we start talking about concavity of a graph. Alright, so we're going to start by just defining the definition of concavity. So many of you may have heard the word concave. So if something is concave, it takes the shape of something like that, where we're going down and then we're going up, kind of a divot almost. So that's something that you might understand as being concave, and then likewise something that's possibly convex could be a bump, perhaps, a mound that could be convex. Well, we're going to define this fairly similarly, but we are going to make some connections with calculus. So if I want to define concavity, I'm going to say that if the graph of a function f lies above all of its tangent lines on an interval, then the graph is going to be concave upward on that interval. So what do I mean? So let's say I have a curve here, and this is going to be a concave up curve, but basically what it's saying is if I've got tangent lines and I'm drawing all of these tangent lines, and if my function is going to be above all of these tangent lines, as you can tell, this graph is above all these tangent lines. These tangents are skimming, and then my function f is going to be somewhere up here, over here, and then it's going to be over here. So it's lying above all of my tangents here. It's above all of my tangents. So if I had an interval, of this, so if this was my interval I, then that would be a concave up function on that interval. Now likewise, if a function f lies below all of its tangent lines on an interval, then the graph is concave down on that interval, or concave downward. So what do I mean by that? So if I have a graph that looks something like this, and I have all of my tangent lines, these aren't really very well drawn, but they're tangent lines. And as you can see, my function is below the tangent line. So if I define this interval I here, between here and here, then my graph, my function would be concave downward on that interval. So that's a brief description of concave upward and concave downward. Now, we've talked a little bit about the tangent lines, but beyond that, we haven't really talked about much calculus here. So, in the past, we've been talking a lot about the first derivative. We've been talking about how we can differentiate to our first derivative. And of course, the process of getting to a first derivative is the same as getting to the second derivative. We just do it twice, and that works for the nth derivative. But we haven't been using it for much apart from the acceleration of an object. Now, the second derivative talks about how the first derivative changes, because it is a rate of change on the rate of change. So it's talking about how our slope changes. And that's really what concavity is. It's how the slope is changing, how the first derivative is changing. So that's the idea behind concavity, and it shows some very important connections with the second derivative. So that kind of leads us to what we call the concavity test, and this is another one of those tests that you are going to want to remember for a while, because this really helps us, again, with developing better shapes of graphs. Of course, concavity, we can have different levels of concavity, and that can allow us to really, really hone in on what a graph looks like, especially a graph, a higher degree polynomial, or a sine wave, or a rational function. It talks about curves. So this is what the concavity test states. it says that if f double prime, that's the second derivative, that could also be written as d squared over dx squared. That's also a second derivative term. You could do f double dot or y double dot or f prime prime. That's not important. What is important is the concavity test. So the concavity test states that if f double prime, my second derivative of my function, is greater than 0 for x on an interval, then that graph is going to be concave upward on that interval. All right. So remember that part, and then we have another part here, which says the same thing for downward, concave downward. So if f double prime of my function x is less than 0 for x on an interval, then the graph is going to be concave downward on that interval. So this is really how we can solve for these concave intervals, very similar to how we were solving for increasing and decreasing values. Just like we could take a derivative, solve for 0, and make our sign chart, we can do the same thing with concavity with the second derivative, although hopefully our polynomials will look a lot more friendly after we've differentiated them more than twice. Alright, so that is our video on concavity. We didn't do many examples, but we will definitely be getting back to this in a more numerical sense. So in the next video, we are going to be introducing an inflection point, the topic inflection points, and we are going to be expanding our knowledge on the second derivative and how it affects the shape of a graph. Thank you for watching, and we will see you in the next video. Please like and subscribe.